Circle geometry, tangents, part 2. We'll start off with 3 screens of exercises, just to practice again. A lot of these are to do with that radius tangent theorem that says that the angle between a radius and a tangent is 90 degrees. But we're bringing in the other radius theorems and a couple of circle theorems as well, other circle theorems. Let's do some answers. In this first case, remember you always say, well, what's x equal to? What is x equal to? I can't find anything. What does x combine with? Well, x combines with that to give you a 2 by exterior angle triangle, or x combines with that and that to give you 180 angle sum triangle. So, in other words, I must either find a2 or a1. Well, this is a radius, that's a tangent. And that means x is 35 degrees by exterior angle triangle. Number 2. We go straight first, say, well, what is x equal to? X is not equal to anything at this stage. Don't say it's equal to this by tan chord, because it's not. This is the angle between a radius, being a tangent and a chord, but the angle will be up there. So we could picture, if you want to be clever, you could say, well, the angle up there, wherever, x is double that. You can go straight there by angle at center, if you can picture an angle up here. Otherwise, you say, well, what does x combine with? It combines with those two to give you 180. So why don't we find that one there? And that combines with this to give 90 degrees by radius tangent. So A1 is 14 degrees, which means B is 14 degrees, which means we can find x by angle sum triangle. We say, what is x equal to? That plus that. And so we need to find this angle here. Well, there's a radius, there's a tangent. In this case, what's x equal to? Oh, nothing. What does x combine with? Well, nothing really at the moment, because all we have is a quadrilateral. We could draw a line there, because then we have tangents from a common point, and we can work that way. Or we could just work with this quadrilateral, because if you're observant, you'll see you have a radius tangent, you have a radius tangent. So there we are. Both of those are 90 degrees. And now we have a quadrilateral. We know 3 of the angles, and we know the angles of a quadrilateral add up to 360 degrees. So we can find x straight away that way. But there are a few other ways to do it. Number 5. We say, well, what is x equal to? Nothing out there. What does x combine with? Well, x combines with these 3 angles to give 180 degrees, or x combines with this angle and here to give you that. In other words, we have to find another one of these 3 angles first. Well, I'm going to go for this one, because have a look, a radius and a tangent. So O2 is 48 degrees, because once we know this, then we can actually find x. O1 is 48 by vertically opposite. B is 90, radius tangent, and therefore x is 42 degrees by angle sum triangle. In number 6, what's x equal to? Oh, it's equal to that angle there. So therefore we can work from there using that fact. B1 is 90 degrees, rad tan, which means we can find O1. Angle sum triangle. And O1 equals that combination where these are radii, so that angle and that angle are equal. X is 25 degrees. What is x equal to? Oh, it's equal to that angle there. And remember, these are tangents from a common point. What do you know about tangents from a common point? They're equal to one another. So we have an isosceles triangle. So AB equals AC, common point. Therefore, x is 65. We say 180 minus 50, 130, halved. There you are. What's x equal to? Well, have a look. There's the tangent. There's the chord. Where's an angle subtended by the chord on the other side? Right there. So x is 130, straight off, if you can pick that up. Number 9. What is x equal to? Well, nothing at the moment, but x does combine with these two other angles to give you 180. So if I knew C2, have a look, there's a diameter. C2 is 90, angle and semicircle. So we can find x by angle sum triangle. Now to find y is not equal to anything there, so we have to find A1 and C1 to use angle sum triangle. But tangent, chord, alternate segments. A1 and C1 are equal to 62 degrees. We don't even need to put tangents from a common point because they're both equal to 62 anyway. Which means y is equal to, I haven't finished that one, 124 degrees, which gives y as 56 degrees. Next one here, what's x equal to? Well, it's subtended by that chord, and on the other side there's the angle. So straight off x is 54 degrees. Now we need to find y. Well, there's a tangent there, and there's a radius there. 90 degrees. Radius tangent. What is x equal to? Well, we're not sure, but x combines with this angle to give you 90 degrees because this is radius tangent there. The y we can easily find because what's y combined with? Y combines with 50 and this 90 to give you 180 degrees. And of course we have these two equal to one another, so we can find that one there to get x. So let's have a look. BC equals CD. There are D1 and B1 are both 65 each by angle sum triangle, isosceles triangle. So x is equal to 90, that 90 minus that 65. Radius tangent, 25 degrees. Y is 40. Well, we know that's 90. We know that's 50. So therefore y is 40 by angle sum triangle. In this next one, what's x equal to? That angle there. What's that angle equal to? That one there by tan chord, but I don't know that one. What else is this equal to? I can't see anything. What does it combine with? Well, it combines with these three angles here. All right. We're not sure about that, but those two are equal to this one here. Do you see the way I explore it to see? I don't say, well, what can I find? What can I find? I try to keep going from the angles I'm trying to find. That is 80. And have a look. This is an exterior angle of that triangle. There we are. D2 is 80. Tan chord. X is 40. Those two add up to 80 and they're equal. Isosceles triangle. So therefore x is 40. Once we know that x is 40, that's 40. And therefore we can find the y. Exterior angle triangle. Oh, we can do it straight away now. 90. And we know that one. Now, let's go on to just one last bit about tangents. We have this situation. If we have that angle equal to that angle, we have a very similar setup to the tangent to a circle, the chord, and then the chord subtending an angle in the alternate segment. So if that equals this, then this is a tangent to that circle. That's what it says to us. There it is there. And this is the converse of tan chord. Let's have a look at an example. Prove that PB is a tangent at B to that circle ABC. Well, let's have a thought process. What if PB is a tangent to that circle? There we are. That angle would have to be equal to that angle. relating it back to the figure, that angle would have to be equal to that angle. So let's find B1 and C to see if they're equal to one another. B1 equals A, 50, reason, alternate angles stating the parallel lines. C equals 50 degrees, reason, isosceles triangle. So we have B1 and C equal. Therefore, tangent, that is a tangent to that circle, and the reason is converse alternate segment theorem, converse tan chord. Try this one yourself first, see if you can do it. Pause and try it, and then go through the answer. We have to prove that RSC is a tangent to circle PQS at S. Well, our thought process, what if? Which means, in other words, what if this was a tangent to this circle? Have a look. If you weren't sure what to do, see if you can carry on from there. We have two options. That angle would equal that angle there. Or this angle would equal this angle there. Either. Can I find that angle there? Yes. Have a look. Parallel lines. So, S5 equals A, equals 25 degrees. What sort of parallel lines situation is this? It's corresponding angles. AB parallel to RC. Q, that one is equal to A. Have a look. There's the bow tie. There's the angles in the same segment. So therefore Q is 25 degrees. So now we've proven that's 25 and that's 25. Which means we have them equal to one another. So straight off now we have that equal to that, and we have the situation we need. Therefore, tangent, there you can picture it. There's the tangent, there's the angle it's equal to. And it's converse tan chord. We still have the practice at Riders coming up.